Okay, welcome back. I hope that you enjoyed the poster/coffee session and ready for our second session for a plenary speaker. And it's our great pleasure to have Giuseppe Notarstefano here today. I will give just a brief bio. Giuseppe got his PhD from University of Padova in 2007, and afterwards he was assistant and associate professor in University of Del Salento. And very recently, actually, from July, he has been now affiliated with the University of Bologna. And Giuseppe had visiting positions in University of Stuttgart, California, Santa Barbara, and University of Colorado. And, finally, I would like to say Giuseppe was a recipient of the ERC staffing grant in 2014. Giuseppe.
So, thank you. So thank you very much for the introduction, and first of all, let me thank Claudio and Ming for this invitation. I have attended other NECSYS, and I really enjoyed this structure of having plenaries, so being on this side is really an honor, so thank you very much for the invitation. So today I will talk about distributed optimization, because it's a topic that has really involved me in the last year with a lot of passion also. Usually when I give talks on distributed optimization, I like to put some initial slides to motivate why I do believe that this is a very exciting topic and a very important topic. But here I will just spend a couple of words because I know that I'm in an audience in which I don't need to motivate it too much. So we all work in distributed computation. We all know that this is an opportunity because nowadays we have really many of these smart devices that constitute an unstructured computation power. And so we are all trying to make our effort to make this unstructured computation power a very structured computation power. So distributed optimization, why? Because optimization is very important, as we all know, because it comes as a building block in many estimation, learning, decision, and control applications. And then we all know, because we are here, that distributed systems, smart networks, are really an opportunity. So what I will do in my first part of the talk, I will try to classify three main distributed optimization setups that I believe are very important. And then I will give you some of our contributions in these three setups with some of the challenges that I believe are very important in this area. So let me start by a very classical problem, and that's a regression problem. We all know you want to fit some curve, you want to minimize some quadratic function, maybe you have some regularizer. And the idea is that nowadays we have really many data, possibly sparse data, spatially distributed. And so what you should do with classical method is just put everything, squeeze everything in this bottleneck and apply some machinery, so you will lose all the structure that you have. So there has been some effort in the late 90s, actually even earlier, in trying to handle these very large-scale problems with the goal of speeding up the computation. And typically the structure that you have in this literature is a parallel structure, a parallel approach, in which you have a very special network structure with a master and clients. So it's a master-client, server-client architecture. There are all these decomposition methods that have been developed. But really the goal there was to speed up the computation. So handle these problems, but with the goal of speeding up the computation with a very special network structure. Whereas we all know that for us, this distributed setting gives us the opportunity to operate in an opportunistic way. So think of processors that only know some of these data, okay? But they don't want to fit a curve based only on their own data. They want to fit a curve based on all the data, okay? So the goal is really to cooperate such that they find the same curve here. In other words, they want to cooperate to solve the global optimization problem. So this example allows me to motivate the first class of problems that I will handle and the first challenge that I want to handle. So sometimes these problems, or in many interesting applications, these problems have a decision variable that is very high dimensional. So for those of you that have been working in distributed optimization, typically I will show you that the algorithms that are present in the literature don't care about the dimension of this X. So the first challenge that I want to address is, what about if this X is really huge dimension? So as I said, this problem allows me to motivate the first setup that I like to call cost-coupled optimization setup, and that is really the one that has been mostly investigated in the literature because it really appears in many applications, both in controls and in signal processing, as you saw. I call it cost-coupled because you want to minimize the sum of functions, all of them functions of the same variable. Maybe you have some common constraint, X, or you may have the intersection of local constraints. So the point is that each agent knows only one local cost function and possibly one constraint. And you want to design a distributed optimization algorithm. What is a distributed optimization algorithm? It's a distributed algorithm. We all know what it is because we are here. So it's local computation plus neighboring communications. And the goal for this setup, let me underline, for this setup, is that each agent has an estimate, a local estimate of an optimal solution, and they want to reach consensus on an optimal solution. So in this setup, the goal for the agent is to agree and reach consensus on an optimal solution. And in fact, I will mention it later, many of the algorithms that have been developed use consensus algorithm, averaging consensus algorithms. And this is just the same slide for the data analytics problem, the sparse regression problem. This is just really some very early literature. I, on purpose, just put very early papers because there are really tons of papers nowadays on this setup with many algorithms, with all kinds of assumptions. But basically, the type of algorithms that you find are either primal methods, so the equivalent of subgradient or gradient methods, but run in a distributed way, combined with a consensus algorithm, or Lagrangian methods, basically dual methods or primal dual methods, or saddle point methods. Jorge is one of those that has been working a lot. And I see Baman here, for example, he has been working on directed version of these methods and many other versions. Okay, so now let me motivate another class of distributed optimization problems. It's really a subclass, or can be seen as a subclass of the previous one, but I want to highlight it as a class per se because it gives us the opportunity to design more efficient algorithms. So consider a problem that is very famous in machine learning, support vector machine. Support vector machine, you find it in many applications like speech recognition or things like that. But the mathematical formulation is very, very simple and intuitive. So you have points in a plane, triangles and circles. They are typically separated or kind of. You may have outliers. And you want to find an optimal separators. So you have points pi with the label li that is either +1 or -1. And when you write the optimization problem, you want to basically maximize this margin. You can write it as the minimization of the square norm plus this, this term here. Oops. Let me skip this version. Okay, sorry. And so the nice thing here is that the cost function is not the sum of functions. It's really a common cost function. And you have many constraints that are associated to the points. You have as many constraints as the points here, okay? So another example of problems that has this same structure is a class of problems like multi-agent task assignment problems. So in this case, you want to, for example, minimize the completion time. You want to find optimal paths for some vehicles. But here in this setup that I'm considering some sort of smart environment in which you have processing units in the environment that know some of the paths that could be chosen. So the optimization, a portion of the optimization variable is a binary vector that selects which path you have to take, and then the completion time is real. So in this case, you have a similar structure, but this allows me to introduce the second challenge that I want to address in my talk, that is sometimes you don't have convex programs or real valued problems. You have problems that are mixed integer. So this is something that you want to handle. It has been handled in centralized optimization. You would like to handle it also in distributed optimization. And this will cover some of the second and third part of my contributions. And so this allows me to motivate this second class of problems that I like to call common cost-coupled problems. So now the agents all know the same cost function, but each one knows one constraint. Okay? And the reason I'm specializing this class of problems is because we really were able to design algorithms that several years ago, when people were working with synchronous distributed algorithms, were already asynchronous with unreliable and directed communication. And I will tell you about these algorithms in the second part of my talk. Again, here, the goal is to reach consensus on an optimal solution. And this is just the same slide for distributed support vector machine for this class of problems. Here, we have been doing some work on this. There are other works, but I'm just mentioning some of our recent work. Not recent, actually, some early work. The third class of problems that I want to touch is a class of problems that has been not really investigated in the distributed optimization literature so much. So there are contributions. I will show some. But it's for sure less investigated. And I think it's a very important class of problems because for us that are in controls, it really models many control applications. I'm giving you an example of smart grid control or smart grid optimization, but there are examples also in cooperative robotics and similar problems. And the idea is that, so in this example, think of smart generators, accumulators, and loads that have some local processing and communications, and they want to optimize generation or consumption of energy. So the idea here is that you have n decision variables or n decision vectors. Each one of them you can think of the input or state of a device. They have some local constraints due to the dynamics and some input saturations, for example, and so on. But then you have a coupling constraint. So here, the cost function is the sum of terms, each one depending only on a local decision vector, decision variable. Each local decision vector has some constraint, but then you have this coupling that couples all the decision vectors. So the coupling comes through the constraints here. And in fact, so yeah, this is just a nice picture to show that you have some sort of cross coupling in the constraints. Again, also here, think of devices that can be just turned on and off. So in this case, again, you can have problems that can be mixed integer because due to this property of the devices. And this example allows me to motivate this third class of problems that I like to call constraint coupled problems. Why constraint coupled? Because there is no coupling in the cost. So each fi is a function of its own xi, but then the coupling comes through this coupling constraint here. As I said, there are very important control applications for this setup. And sometimes they are part of MPC schemes. So you want to really solve this problem in a distributed way, in a very fast way, and with some guaranteed feasibility. But here, let's think about the solution, the distributed solution of this problem. So in these problems, you don't want to reach consensus anymore. when you want to solve this problem in a distributed way. So you would like each agent estimate to converge to just its portion of the optimal solution. So now the decision variable is this x1, xn. You don't want all the agents to reach consensus on x1 star, xn star. You want agent I to compute the portion xi star of the solution. And in fact, you could convert cost-coupled problems in this setup. But in that way, if you apply algorithms for cost-coupled problem, you would run an algorithm that reaches consensus on the entire x1 and xn. And you don't want to do that. Okay? You would prefer to have some privacy also in the solution. And again, this is the same slide for the smart grid control example that I gave. As I said, there is less literature. We have been working on this, and I will show some work that we have done that covers also the mixed integer challenge. So to sum up, in distributed optimization, we have an optimization problem. Each agent only knows a portion of this optimization problem, but they want to solve the entire optimization problem cooperatively. So here we are considering networks that are cooperative, so agents collaborate. And there are many challenges, and the one that I want to highlight are, the first one is very common to all distributed algorithms. So we really would like to have an unstructured network in which there are packet losses, direct communication, and so on. So asynchronicity and unreliable communication. As I said, there can be problems that we like to call big data in the sense that the decision variable is huge. Okay, and I will cover this. And then you can have non-convex mixed integer problems. And sometimes you want to solve this problem with fast algorithms because you want to run them in real time. Again, I don't have to convince you, but we have no central coordinator. We all know because we are here. And we cannot design the network. So the network is given by the application. Okay, that's what we want to do. Okay, so I will sketch 3 contributions that we have given to answer these 3 challenges that I mentioned. So first of all, I will consider cost-coupled problems that are big data in the sense that the decision variable is huge. And so I will show you some contribution that we have given, some algorithm that works blockwise. In the second part, I will cover common cost problems, and I will show this class of methods that I call constraint exchange methods that allow you to have this very general communication structure. And, and we also addressed mixed integer linear programs with an extension of these methods. And finally, I will show you some algorithm that we developed for constraint coupled problems. And very recently, we also did some work that we will present at next CDC for mixed integer LPs. Okay, so this will be basically the rest of my talk. Okay, so the first part, this distributed big data optimization setup, this is a very nice collaboration with the group of Gesualdo Scutari at Purdue University. And I also want to thank my postdoc and former PhD student Ivano that did a lot of work on this together with Hing. So what is the problem here, the challenge? So you have a cost-coupled problem. This is the first class of problems that I presented. So sum of functions, all of them function of the same vector. Here we also added some regularizer terms, some common constraint. But here the challenge is really that the decision variable is huge. So you have many blocks. So think of this B as a very high number. And the idea is that you don't want to optimize on the entire vector. You don't want to communicate the entire vector to the neighbors, because that could be too much. Okay? These are some assumptions that we put on the problem and on the network. So what is the algorithm that we used? We basically started from an algorithm that has been really widely investigated for non-big data problems. It's this idea that is called gradient tracking that I will briefly summarize. Depending on the different versions, they gave it very different names. Probably one of the first that appeared was this next, and then the directed version, this Sonata, that basically we took inspiration from. So what is this gradient tracking idea? So now think of a non-big data problem. So the decision, you don't care the dimension of the decision vector. So it can be a scalar, okay? So you want to solve this problem. Basically, you want to design a distributed algorithm such that all the agents reach consensus on a solution of this problem here. So what you do, so you do a two-step procedure. So in the first step, so what would you do in a centralized setup? In a centralized setup, you would design a gradient algorithm, something like xt plus 1 equal to xt minus the gradient of the function. And the gradient of the function is the sum of the gradients of the fi. But an agent doesn't know the gradient. So what you do is you do a descent step on a local estimate. So this xi of t is a local estimate of the solution. And you do a descent step along some direction. What is this direction yjt? Is basically a local estimate of the entire gradient. So in the first step, you do a descent along this direction that is a local estimate of the whole gradient, and then you mix everything with an average consensus. And in the second step, you basically what you do is you want each yi to track this global gradient, and you do it with this gradient tracking or running consensus scheme that was developed for a general version of signals by Zhu and Martinez, and allows you to have this yit to converge to this sum of the gradient. So this is the idea, basically. These are some assumptions. In this setup, you have the matrix that needs to be doubly stochastic. But I will tell you why in the next slides. We needed to work with directed communication. And if you want to work with directed communication, here is crucial that this consensus is not just a consensus, but it's an average consensus. And so since we needed to work with directed communication, if you want to do this tracking of the average of a signal in directed networks, then you have to apply a scheme that is known as a push sum. So basically, you need an auxiliary variable, then you need to construct weights that are not doubly stochastic anymore, but they are column stochastic, and then you need to do this ratio between this quantity and this phi t plus 1. So it's called push sum consensus. It's very well known now in the literature. And basically, if you run this scheme, you can do the tracking of the average in directed networks. Okay? So what you do for gradient tracking in directed networks is basically that you replace the usual average consensus with this push sum average consensus. Okay? So it's the same scheme that I presented before, but I just replaced the consensus with the push sum consensus. Okay, so why did I recall this method? Because basically what we did was a blockwise version of this method. So let's go back to the setup, to the big data setup. And to explain the idea, I will just consider an unconstrained case. Okay? So there is no constraint, there is no regularizer, just to explain better the idea as before. Okay, so again, let me recall that if we have the decision variable that is is a huge vector, then we want to operate only on a block of this decision variable. So we want to minimize over a block, and we want to communicate only just one block. So the idea, so what happens when you want to communicate only one block is that if you apply some sort of essentially cyclic rule, so you pick a block each time, but you have to be sure that all the blocks are taken in a window, then what happens is that you get an induced graph over each block. So in this picture, I'm considering two blocks. So this agent is considering at iteration t this first block. All the other agents are considering the second block. And here, vice versa. And as you can see, there is a directed graph that is induced on each block. There is the red graph and the green graph. And this is just I'm just formalizing that. And the very important point, this is why I had to bother you with this push sum consensus idea, is that even if you choose the underlying graph to be undirected, then this graph is directed. When the block-induced graph is directed. That's why I had to bother you with this push sum idea on the blockwise consensus. So what we did, the first thing that we did was to basically design a blockwise version of this running consensus. So these are exactly the same equation that I showed you a couple of slides before. But now this L means that you do this push sum only blockwise on the Lth block. And the nice thing is that this idea is kind of very intuitive. So what would you do if you have a push sum consensus algorithm and you want to design a blockwise version? You try to implement it in a blockwise sense. And the nice thing is that it works. We were able to show that it works and that agents can build these weights locally, basically. And so the algorithm, the distributed optimization algorithm now is a two-step. Again, we were driven by the intuition. So let's do the descent direction blockwise. So instead of taking minus yi, the entire estimate, we just take one block. And then let's do the averaging and the gradient tracking blockwise. Okay, so from a, let's say, an intuitive point of view, the design of the algorithm was kind of easy to think of, but then, of course, proving it was much harder. And we proved it on a more general setting in which you compute the descent direction, in fact, as an optimization problem, because you may have local constraints and you can choose, instead of just computing a gradient, you can do what is called successive convex approximation. This was really something that Aldo Scutari had developed for a non-big data case, so we took his machinery and we extended it on together on this blockwise version. And so what we were able to show, as I said, there are many technical challenges, even if the intuition of the algorithm is quite nice and simple. We were able to show that agents reach consensus on a weighted average, and then that any limit point of this weighted average is a stationary solution. So in fact, the agents reach the goal blockwise. So they don't have to communicate the entire vector, they just have to communicate blocks. So again, let me stress this. I think this distributed big data optimization setup is a very interesting setup to investigate it. We just put a first stone, but there is a lot of work to do here, I think. Let me move to the second part. So I want to address this common cost setup, and I want to show you some methods that I call constraint exchange methods. It will be clear in a couple of slides why they are called this way. And then I will show some algorithm that we designed for mixed integer linear programs, and this is really a work of my students Alessandro and Andrea. Again, let me recall this cost-coupled setup. Here, I'm considering the common cost to be linear, but this is without loss of generality. You can show that you can have any nonlinear function here. And here, I draw these sets because it's really the important information that is stored by an agent is a set. And in this case, I'm considering a convex program. So in order to give an intuition on the algorithmic idea that I will show you in the next slide, let me take a linear program. So if you want to solve a linear program, so imagine that you want to minimize C transpose X, so along this vertical direction, subject to these n constraints. So let's say that we are in dimension 2, but you have like 1 billion of constraints. Even if you have really many constraints and you are in dimension 2, the solution is always characterized by at most 2 constraints. That's the key feature of linear programs. And actually, these active constraints are called the basis of the problem. Okay? And you can generalize this concept of a basis to convex programs, but also to a much larger class of problems that we found in the literature and that are called abstract programs. But the idea then in a distributed setup was, okay, instead of designing an algorithm that keeps a solution estimate, a vector, and exchanges a vector, let's try to keep a basis estimate and exchange basis estimates so that the goal will be to reach a consensus on an optimal basis. This is really the idea that we had when we thought of this algorithm. And this is what we call constraint consensus algorithms, because you really make a consensus on the active constraints on the optimal basis. So you have a state, each agent has a state locally that is a candidate basis. So think of those two constraints, those two active constraints. You want to reach consensus on them. And then in the evolution, what they do is they collect bases from the neighbors. They use their own basis and their original set. Remember that at the beginning you had a local set. And then you solve a local version of the problem on this H-temp, which is basically a constraint set including only your neighboring basis, your basis, and your original set. And even though I put this time t here, you can really do it in a very asynchronous way. So you just do the computation when you are allowed to do or when you can do it, and you just send the basis to the neighbors. And even if the communication doesn't go through, you don't care. Even if you don't receive, you don't care. Because the key is that really we were able to show that this algorithm works in a very general network setup. So this is what we call constraint consensus. As I said, it works for a much more general class of problems called abstract programs. Then we had a very nice collaboration with the group of Frank Algoover and with his PhD student Matthias Bürger that I kind of co-advised. And we did some extension using polyhedral approximation, cutting planes. And recently we have been working on other extensions, uncertain problems, so problems in which the constraint set are uncertain, some combinatorial problems. We have some work at NECSYS on submodular optimization, and mixed integer programs. And this is the one that I will show you today. So let's go back to the cost-coupled problems and constraints again, common cost function, but now you have this mixed integer constraint. Okay? So you have not a linear program or a convex program anymore, so you have a mixed integer problem. So how did we approach this problem? We looked at the literature. And if you go to the literature, there is a nice class of methods that are called cutting plane methods. It's really an approach. Then everybody has its own method depending on how the cutting planes are constructed. But the idea is the following. So you take the constraint set. So this gray area is the non-mixed integer one. So just the set, the intersection of the linear constraints. In this case, I'm considering the horizontal vector to be the integer variable and the vertical vector to be a real variable. Okay? So the feasible set are these red lines. So think of this as 0, 1, 2, and so on and so forth. So on the vertical axis, you can have any real value, but this is quantized on the original axis. So the red lines are the feasible set. So if you do a convex all of these red lines, you get this other set. And the nice property is that if you minimize on the blue set, on this convo pi, then you get the same cost. And in particular, some of the solutions are mixed integer. So the way people proceed in the literature is to try to approximate this blue area with cutting planes. And this is really this cutting plane approach that you find in the centralized literature. So you start from the gray set and you compute a solution of the LP. It's this one. So you check if it's feasible. If it's on the red lines, it's not, then you move on and you make a cut. And I will tell you something about these cuts. You compute again a solution. It's not feasible. You make another cut. And you compute a solution. Now it's feasible, and then you go out. This is a solution of your last LP, but it's also a solution of your mixed integer problem. Let's go back to the distributed setup. How did we come up with a distributed version of this algorithm? Basically, we decided to mix the constraint exchange idea, the constraint consensus idea, with this cutting plane generation idea. So we assume that each agent has an LP solver. So locally, an agent can solve an LP. So it doesn't have to solve the mixed integer version of the problem, just a relaxation of the problem. Okay? And it can compute a basis. So this is the optimal point, is xi, and then it can compute a basis, but for an LP, for a linear program. Then the other routine, local routine that an agent has is to generate cuts. And in particular, we used these mixed integer Gomori cuts, which are very famous in the mixed integer optimization literature. So the first cutting plane algorithms that came out in the literature were based on these cuts. And then some other cuts that are called cost-based cuts that are generated based on the current cost of the problem. So we mixed them together, and we came up with an algorithm that we called int decut milp. The int is because this first version of the algorithm works when you assume that the cost is integer. Okay? And the idea is very similar to the previous one. So the idea is the following. So you initialize your local basis. Okay? Then you generate this Gomori cut and this cost cut. This does basically a rounding of the cost to the next integer. That's why we need the assumption that the cost is integer, that we need to cut at the next integer. Then you collect the basis of your neighbors. You put your basis, and you also add all these cuts that you have generated. And then you solve the LP relaxation. So again, a node just needs to solve an LP relaxation. And what we were able to prove is that under this very general communication structure, so just jointly strongly connected graph is really the most general one that you can think, and integer optimal cost, then in finite time, in a finite number of communication rounds, the agents agree on an optimal solution of the problem. Actually, they agree on the lex optimal solution. So we had to use this lexicographic ordering to prove the result. Now, what about if you have a general problem? So I said that this algorithm, this version of the algorithm works if you assume that the cost is integer. Assuming the cost is integer, for example, all the integer programs, basically, if you choose integer weights, fall in this class. What about if you have a general problem? So we came up with an idea that goes through an epigraph formulation of the problem. So basically, this problem here is the same problem, equivalent, but in an epigraph formulation. So this is, you had this constraint, C transpose X less than or equal to rho. So this rho is a slack variable that plays the role of the cost. Okay? So this is equivalent, but here the cost is again real. So what we did was to do a quantization of the cost. So you assume that this rho is some epsilon rho I, where this rho I now is integer. Okay? And then in some sense, you are getting a problem that is not equivalent, but it's some sort of relaxation that allows you to get epsilon close. So what we were able to prove is that if you solve this problem, you find an epsilon suboptimal solution. And in fact, the idea was really to design the same algorithm. I will not describe it because it's exactly the same as before, but on this problem here. And to be honest, we were not able to find this idea in the literature. So in principle, one could apply this algorithm also in a centralized setup or in a parallel setup. I don't know, maybe someone else thought of it, but we didn't find it. And this is the result. Basically, we removed the assumption that you have integer cost, and you get to a suboptimal solution. This is some sort of common practice in the centralized literature of mixed integer programming. So try to find the epsilon suboptimal solution, because these are really NPR problems. Let me just stress once more that this class of algorithms, I like them a lot because you could really go and implement on devices. For example, we ran some simulation in the paper with packet losses, and even with 90% of packet losses, the convergence was slowed down, but the algorithm was working nicely. Because really, behind the proof, there is this argument that allows you also to lose packets through the algorithm. Okay, so very last part of my talk. How many time do I have? I have some time. As I said, this constraint-coupled setup, I think it's very important, but it has been less investigated. So we did some work designing an algorithm for convex programs, and very recently extended it to mixed integer programs. So this is a work of my students, Ivano and Andrea. In particular, Ivano contributed to the first one, and the two of them to the second one. So again, let's go back to the setup. So just to be sure that we remember the problem that we want to solve. So we have this problem in which we want to minimize the sum of functions. Each one is a function of a local decision variable, xi. This xi is locally constrained, but then there is a coupling that couples all the variables. Okay? And we want to solve it in a distributed way in the sense that each agent needs to find the xi star, not all the other ones. The assumptions that we need here, so here we were working with undirected and fixed graphs, but we are also extending it to time-varying graphs. And plus we need this condition that is basically some sort of Slater condition, because as you will see, we will work with duality here. Okay, so let me show you the algorithm first. It will be not clear why it works, but let's look at the algorithm from an intuitive point of view, and then I will show you the tour that we made to get to this algorithm. So each agent basically has an estimate of the decision variable, this xi, of its own decision variable, this xi, plus it has this slack variable rho I. I will tell you in a second what that is. And then two types of dual variables, this mu I and this lambda ij. They are dual variables at different levels. We will see that. Okay? So what are the updates? So basically what each agent does is that it solves this optimization problem that is some sort of local copy of the global optimization problem. So let's look at this copy. What is the structure of this local problem? So instead of having the sum of all the gi less than or equal to 0, since agent I doesn't know the other gj for j different from I, he has this local constraint that is gi of xi plus this term here that somehow replaces the missing part. And then instead of having a hard constraint less than or equal to 0, we allow some local violation, and we penalize this violation here. So there are two important features here. You replace the missing part with this term, and then you allow some local violation at each step. Okay? And then what happens is that, so you compute a primal dual solution of this problem, and then you update this lambda ij. Look at this step. This is some sort, for those of you that know dual decomposition, this looks really like a descent step, and it's really that in dual decomposition, because you have lambda ijt plus 1 equal to lambda ijt minus some step size, and these are basically a subgradient. This difference is a subgradient. Okay? Okay, so just some intuition. I gave you a bit of intuition, but let's remark it. So this term here, this sum of where j in an I of this lambda ijt minus lambda ji of t, you can think of it as some sort of allocation vector, this minus yi of t, that allocates to agent I the portion that, some sort of portion that is allowed to use. So he can use gi of xi, but he has this portion allocated by the other agents. Remember, try to remember this yi of t that is basically all this sum, because I will use it later. And so, as I said, we allow some violation, okay? And then we penalize this violation. So this is the intuition behind the algorithm. Now, how did we come up to this algorithm here? So basically, since we were working with this kind of new setup, so all the people have been working on this cost-coupled setup that I showed you at the beginning. So we said, and in that setup, in distributed optimization, using duality is really useful to design distributed algorithms. So we said, okay, let's try to apply duality to this problem. So we computed the dual of this problem. This is a convex problem. Strong duality holds. So you compute the Lagrangian of the problem, and you compute the dual function minimizing the Lagrangian over x. You can put the minimization inside because everything is decoupled, and you get this dual problem. So if you look at this dual problem now, it has a very nice, interesting structure because it's a cost-coupled problem. So it's the sum of functions, qi, all functions of the same mu, common variable. So then we said, okay, let's try to apply some algorithms that are available in the literature to this problem. And in fact, some of the algorithms in the literature that I showed you apply distributed subgradient here, but we did another choice, a different choice. So but before moving to the next step, what we had to do was to add a restriction on the dual variable. So this simplex constraint is basically bounding the mu on top. Why did we add this? At the beginning, we didn't add this. We proceeded with the next step that I will show you in a while, but then we had to stop, and I will tell you why. So we needed to add this restriction on the mu, and then we asked ourselves, what does it mean adding a restriction on the dual problem? If you go back to the primal, adding a restriction on the dual problem means relaxing the primal problem. So that's why you get a relaxation in that distributed algorithm that we have. So this raw variable appears in the cost and as a relaxation of the constraint. Okay, so I didn't tell you why we needed this restriction, but let's say that we have this restriction. How did we proceed? We said, okay, let's apply what is known in the distributed optimization literature as dual decomposition for this problem. So basically, we made copies of this common variable mu, so mu1, mu_n, and we enforced that all these copies are equal, but only if there is an edge between I and j. This is not something that we invented. This is something that you find in cost-coupled optimization problems. There is a very nice tutorial by Michael Johansson on this technique. So once you have designed this equivalent problem, then you can show that if you dualize this problem, you get another problem. That's why we call it a duality tool, because we were really applying duality again and again several times. You get this problem here, and then what you can do is applying a distributed subgradient on this problem here. But here is where we got in trouble without the restriction here. So if we were trying to apply the distributed subgradient here, the domain of the lambda was not the entire space, so we had problems in doing that. And what was the reason? The reason was that some of the local problems got unfeasible at some point. So allowing the relaxation was somehow the trick. And basically what we were able to show using min-max and max-min optimization was that this one is the way you compute a subgradient of these local functions. So this is somehow the intuition. So you find all the details in these papers in this paper that we just submitted, and that is on archive. So the result that we were able to show was that not only we have cost optimality, so this is saying that even if you have this rho I of t in the cost, this is squeezing to 0 and the cost is converging to f star. But even more importantly, we were able to prove that the primal sequence that you have, that converges to an optimal solution. And this was not obvious at all, really, when we started to prove this result, because people that work with duality know that when you apply dual methods, if you don't have strict convexity in the original cost, then recovering the primal sequence is quite hard. You need some, they are called averaging mechanism. So in this case, we didn't need any averaging mechanism. And in fact, we got an even faster algorithm for this reason. So the nice thing is that this sequence converges to the optimal one. That was a very nice result that we put. So these are some interesting features of the algorithm. So it's scalable because each agent only computes its own xi star. It's private because you don't need to exchange your estimate. If you remember the table that I gave, you just need to exchange those dual variables. And plus, I want to stress this part because, to be honest, we had some problems in convincing some of the reviewers that this algorithm was interesting. And one of the objections was you can just make a distributed subgradient on the dual. And we were trying to answer this reviewer, no, it's not, because it will be very slow, that algorithm. Our algorithm is much faster because it doesn't do this recovery mechanism. So I want to point it out. OK, so now, what about if instead of having a convex program, now you have a mixed integer program? Now the constraint is linear, but the challenge is that this set xi is mixed integer. So if it's mixed integer, you don't have strong duality anymore. So you cannot apply that mechanism just in a straight way. So what you can do is to try to come up with some epsilon suboptimal solution, some suboptimal solution with some guarantee, let's say, some suboptimality guarantee. So what we did was, actually, we look at the literature, there was already partly this idea. So you convexify the local constraint, but if you convexify the local constraint, this problem is not equivalent because you are not convexifying the coupling constraint. So this is a relaxation of the mixed integer linear program. But this relaxation can be solved with the algorithm that I just showed, this RSDD algorithm. Okay? So now the idea to approximate an optimal solution is the following, the one that we developed. This is the same algorithm that I just showed, but I replaced that term sum over j with the YIT. Remember I said, remember this YIT. So this part is something that you apply to the relaxation, but with a restriction. This is something that people in MPC do very well. You do a restriction so that you can violate with the restriction and satisfy the original constraint. So then once you have run this algorithm, at the end, basically, you can compute a mixed integer locally by solving a local mixed integer version of this problem. You could solve it only at steady state. You don't need to solve it at each iteration. But the nice thing is that when you solve this problem, when agents solve this problem, many of these solutions will be already mixed integer. Some of them will not be. So you will violate, so this row will be something that violates, but then what we were able to show is that that restriction that we put with the violation allowed us to have feasibility. And this restriction is quite tight because the intuition was the restriction that you need to apply is just the minimum space that you need at one agent for one feasible solution. Okay, so in some sense, this gave us a tight restriction because you don't have to find a large restriction. You have to find just the minimum amount of space that you need. And I mean, for those of you that will be at CDC, there will be many details there on the idea of the technique and the line of proofs there. I just wanted to give a sketch here. I'm almost at the end. There are these challenges that we have been addressing, they are in some papers that we have submitted. You find more on the website of the project. I want to thank my group, even though not all of them have contributed to this part of the work that I just explained. A special thank to a couple of guys, to Ivano. As you saw, he was in many of the works and he gave me a very useful hand in preparing the slides, and also Andrea is a very good English writer, and so he did also some English spell checking, but also some help in designing the slides. With that, I'm almost done. I just want to summarize what I think are the main features that make distributed optimization a very fascinating and challenging environment or research area. So I think that we really have out there the technology for computation and communication. There are many optimization problems. So optimization is really a key area in many engineering problems and other areas. But in distributed computation, we need really to still address many challenges. In particular, the ones that I want to underline are that the network must be really unstructured. So asynchronous communication unreliable, because otherwise it's not really what we want from this distributed computation framework. Problems can be very complex, mixed integer, combinatorial, non-convex. There is a lot of work to do on many classes of problems, many general classes of problems. And as I showed you, problems in which the decision variable is very huge, that's really, I think, an interesting challenge as well. So with this, I think I'm done. Thank you for listening.
Thank you, Giuseppe, for this nice talk. And now it's time for questions.
Hi, thanks for the nice talk. I'm wondering whether the data that you feed into the algorithm is thought of as affected by noise of some sorts. That's something I mean I might have missed. So please tell me whether that was in the content here, and if not, what is the perspective on this matter?
Okay, so let me try to see if I understood the question. So if I understand the question you are saying, you get an optimization problem. Think of, for example, this sparse regression problem because you have data. Okay, but this data may be affected by noise. Okay, this is a very interesting question because in that case you have an uncertain optimization problem. Okay, and this is really, I think, another class of problems that needs a lot of investigation. So you get what are called uncertain optimization problems. It's also called robust optimization. And you need to develop methods that take into account the possibility of having uncertain in the constraints. So you have basically parameterized constraints or parameterized cost functions, and these parameters are uncertain, are bounded in some set. Okay, so these problems are uncertain. So what people do, for example, there is the group by Roberto Tempo and Fabrizio Dabbene that worked a lot on this randomized method for uncertain optimization, this scenario approach and so on. So you can kind of do something similar in a distributed setup. We did some work on some robust LP, and we are doing something on some robust mixed integer programming. If I understood the question. If the question is when you run the algorithm, there is uncertainty when you communicate. No, okay. So the question was that, yeah, there is this class of uncertain optimization problems, and one of the approaches is to do randomized methods. And yeah, I think it's a very interesting and open area, that one.
Okay. Are there any further questions? If not, we would like to thank the speaker by this gift on behalf of the organizing committee.
Thank you very much. Thank you.